Welcome to an ASEG technical talk. I'm Baba Kajani, and today is the first in a series of exciting talks that we have organized for you from a wide range of geosciences. Today's talk is by Dr. Desmond FitzGerald, and it's titled, Can Airborne Geophysics Play a Role in Exploring for Natural Hydrogen? Desmond FitzGerald is a founder and now former director of the Intrepid group of companies. Des has a bachelor degree from 1969 and a PhD in mining 1977, both from University of Melbourne. And Des co-wrote the Intrepid geophysical processing and mapping software. So before we start, I would like to acknowledge the country. The ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We're talking to you from Canberra, and that's the land of the Ngunnawal Ngambri people. We recognize their continuing connection to these lands, water, and culture, and pay our respect to their elders, past and present. Slides are not good. Here we go. Just a thank you to our corporate members and to our brand sponsors for their continuing support. We are doing this in a hybrid mode, so those of you for in person attending in person, and those of you online, please mute your mics so that there's no interruption during the talk. If you have any questions, please click on the chat button and put in your questions and comments for this, please. Thank you. Just going through housekeeping, please consider becoming a member at the ASEG if you're not a member already. You get free access to exploration geophysics, which give you access to high quality research results and relevant case studies in ASEG technical journals. You get a free copy of Preview, which helps you to stay up to date with the current trends in exploration geophysics. You get reduced entry to AEGC conferences. You get a free entry to regular technical talks in your state, such as this one, and access to job advertisement posted on ASEG website. You get access to annual wine offer, amazing, and you get social events, invited to social events in your state, which helps you with networking, so fostering a professional network. You also get access to research funding and travel scholarships that we have for students, and it's a free membership for students and half price for retirees and recent graduates. And keep in touch. Please follow us on our social media network accounts and visit aseg.org.au/events for upcoming events. And with that, I'll give it up to Des. Thank you.
Good afternoon, everybody. I'll just click up the first slide, make sure I can do that. So the background to this talk is that in retirement or semi-retirement, my brain was still active, I noticed, and I was training one of the young geophysicists in the business, who's since moved on. So, and we got there's the first natural hydrogen explorer in Perth, organised by Isabella Moretti, who I'd met in Vienna 18 months before or 12 months before, and it struck me in the workshop the EAG put on that geophysics wasn't present and wasn't even on the radar for the geochemists who had been doing the field work looking for occurrences of natural hydrogen and she started showing all these Australian case studies, even though she's in France, Italy and all the rest of it. The Europeans are coming to Australia because of all the data and the access to, all the background. So I thought, oh, well, I put my hand up and I immediately at the workshop, I said to Isabella, have you ever thought about the possibility of geophysics playing a role in this exploration for hydrogen? and she didn't say no, but when I saw she was organising a conference in Perth, she kindly opened up a slot, and I was using that to train someone, and I'm happy to train someone else who's interested in taking this forward as one of my, I don't know, legacy or gifts to the industry, because I think there's a lot of scope for development here. Anyway, that's the background. And you see the saga thing. I have a business in Namibia still. Anyway, it was supposed to be bought from me, but it's not. So I'm going over to Namibia to the SAGA conference, the South African Geophysical Association, and that's in about 6 or 8 weeks. And I note there's Louis on the line. He's from South Africa. But this will be the same talk, Louis. So if you catch it here, you'll catch it in Africa as well. Anyway, moving on. So that's my name, and one of the companies I still own is still there. And this is with reference to Chris, I think. Yeah, Chris is in the audience. I didn't realise he'd show up. So I beg borrowing and stealing one of your maps, mate, is the first thing we show. And Isabella was using this as well, of course. And anyway, the question is why is it we never even thought, as a collective? I'm talking collectively, and if I'm wrong, shoot me down. I don't mind being interrupted. I don't mind you saying whatever you like to say on the cuff, or you can hold back and be more polite. I don't mind. I take it as a compliment if you get so upset about something I say that you immediately say it. I'm happy about that. But anyway, the question here is, can standard airborne geophysics methods be upgraded, or can they be used as they are to join in this search and to make a contribution? So far, natural hydrogen has been discovered as a byproduct mostly of hydrocarbon type targeting. And there's a huge long history of that, goes back more than 100 years. Kangaroo Island, 1922 or something, the bore there that still flows at 2% hydrogen. It's amazing. But we've ignored all that. So let's look at these existing known cases that Chris has kindly made a record of in this map. And it's not the only map, but it's a good start. And because I'm talking to this is a tryout for the African conference, so I make no apology, but saying I'm going to at least reference Southern Africa in the talk and try and talk about the two cases and how the lessons learned in Australia might apply in Africa as well. So in particular, it's Namibia, so it's even better, and the Damara belt. How do I let someone in? You're doing that. Okay, that's great. I don't want to have to do that as well. So I'll just move on. Yeah, already acknowledged reference. So let's just talk to the subject. So can we just use existing practice, or do we have to slightly improve? And my answer to that is we always should be improving, trying to improve. So even if it's not necessary, I would still push that we should try and improve practice. And this is a suitable challenge for that. So, and as I said there, no one's really used geophysics remote sensing technology particularly to find it. And yeah, so our best hope is identifying the thumbnails or the signatures that mineral alteration, which involves hydrogen production, or as it turned, that's the near surface stuff, or identifying these natural chimneys or vents where you build up the pressure from deep crustal or wherever, and they start to vent, and you get these chimneys occurring, and surely we can find those using geophysics methods. So and of course, this is analogous to the diamond pipe problem, the kimberlite, and that's famous in geophysics, potential field geophysics. It's not new, at least 15 years, and out of the Canadian Geological Survey, Pierre Keating came up with his method, and of course oil deconvolution type methods are also applicable. So there's off-the-shelf stuff we already know that we've tried that works okay. And I'm asking, it is possible to convert standard TMI into mineral to magnetic tensor gradient form. It's just a Fourier transform. And I'll show you a little bit of that. So it's all existing, and perhaps if we fly slow and we fly low, can the drone technology, which is existing, somehow have a place? They're just questions. Now, moving forward, without taking much more of a step from where we are today, can we upgrade the survey instrument to actually be a mag tensor gradient instrument? Because that's available in Africa today and is very suited, I think, and I'm hoping I'm demonstrating that with one of my little examples. And can we also improve? You may recall, if you read your previews diligently, last year I wrote a thing called the Sliding Doors article about how for 20 years, even with Peter Gunn beating me over the head, we ignored some of the possibilities in the maths and the physics for doing a better job. And it turns out there's this French mathematician called Cauchy 200 years ago who invented all the theory, and as practitioners, we've completely ignored it to date. And does that have a place to pay? I'll show you some examples. And of course, the other big thing that we're facing as an industry or a profession is the need for the person with all the experience, like me or Ted or others in the room, or Mike, where you learn to eyeball and give an opinion. We now have to work out how do we take that human learning and make it somehow codify it and make it suitable for machine learning. So the whole switch from quantitative to qualitative is an ongoing pressure which we all feel and we somehow got to respond to. And if we're of the mind, we want to do something about it, that's applicable here in this improvement story. So what is this Cauchy thing all about? So it's a solution that's not only developed by Intrepid Geophysics, but Jeff Thurston over in Canada came to me with this idea a couple of years ago. And it stems exactly with what Peter Gunn was pushing 20 years ago, where you take the real signal, I'll point at it. That's like the standard time series along the profile. You take if we come back to the microphone, you take the Hilbert transform of it, put them together in a complex note, and you get this squiggly trace as a time series. It's a complex number. And from that, if you go through the maths, it ends up preserving the higher frequencies and is a much more, gives you much more possibilities. I'll give you a quick illustration of that as we go forward. So just take a typical ground gravity grid. This is just an illustration of the benefits. And you take a first order derivative using what's called the finite impulse response Fourier technique, and that works. Take the second derivative, starts to go shit, and then take the third derivative and you're in deep trouble. It doesn't work. Whereas if you use this Cauchy approach, one hopes it's coming, you manage to retain the coherence of your signal. So for 20 years, all of the potential field geophysicists in the world have put up with this and not recognising that there was a proper simple way out of this. And that's why we called it the sliding doors moment. There is a way of going forward. And, you know, I have to apologise for being so slow to get it and start to promote it. It took a long time for the penny to drop that this was available and that we should convert all of our methods to use these sorts of ideas. The old excuse, oh, it's complex, no, too complicated. Computers can't cope. That's bullshit. The computers can do it in less than a millisecond without missing a beat. So all of our methods in potential field geophysics should take note of this old insight that we've ignored. So now to move on to the topic of the day, and taking Isabella's lead of Australian case studies. So we picked out 3 Australian case studies, and we want to have a look at examples for the known hydrogen production mechanisms and pick out the 3. So pentonisation, which is associated with deep continental tectonics. So it's It's famous academically, but not famous particularly in the commercial world. Weathering, it's famous everywhere. And you can get with weathering of banded iron formations, natural hydrogen is a byproduct. And then, of course, when you have deep earth processes which give off gamma rays or alpha and beta, you get, and that interacts with water in particular, radiolysis occurs and hydrogen is liberated. So there are 3 Australian case studies where you can pick an example of each. That's what I'm going to show you about. And none of this is particularly novel. They're well-studied areas in Australia where the geology is well known. The geophysics data has been available forever. It's just a case of trying to use this as to can we zero in and usefully make some contributions. And I'm going to mostly ignore everything except aeromagnetic. Start at the basics, and we're going to go with that. So a little bit more on serpentinization. It's the hydrolysis and transform of ferromagnesium minerals into ferromagnetic minerals, and usually in the context of very high pressures and temperatures, therefore tectonics. And hydrogen is formed in the oxidation. So the ferrous iron or iron ore minerals is implicated or are implicated here. And then you get, there it is in the chemistry coming out, olivines, pyroxene, leading to magnetite. So that's the classic sort of definition. Moving on, what is radiolysis? The same sort of thing. What is it? So it's a dissociation of the molecules by radiation. Just you're hammering the basic molecules with high energy particle physics, and some of the bonds give up. And so radiolytic splitting of water is the primary case. That's the most common case. And once again, you break up the water naturally, and hydrogen is one of the. So what's in the geological setting in Australia, well, we've got to look, you look no further than South Australia as soon as you say this sort of stuff, because the South Australian heat anomaly, the well-known South Australian heat anomaly, is another reflection of exactly the same deep background, low-level radioactive. There's a nuclear reaction sitting under the whole of South Australia because of that failed rift, I suppose. I'm not going to go into the theory of why it's there and exactly all the rest of it, but all the way from Kangaroo's Island all the way up to Amadeus Basin, there's manifestations of this phenomena, and it's including the heat anomaly. So there's something big going on there, and we've all known about it. And lo and behold, hydrogen is anywhere in that area, the York Peninsula, Kangaroo Island, up into the Amadeus. It's all very prospective for natural hydrogen. So the 3 case studies, one for each, picked on the Darling Fault and the township of Moore in Western Australia. And for the weathering case, the redox weathering case, picked on the Brockman syncline, and radiolysis, the Amadeus Basin. So every one of these has had a lot of work. There are 3D geology models, there's stratigraphic piles, all the base data is available, they've been studied over the last 10 years, nothing particularly new in terms of, there's known geology more or less at the group level, and the automation's there and all that, and the data, the geophysics data's there, so they're great for training and for testing and for general stirring the pot on this subject. There we go. So why Moora? For serpentinization to occur, you need an iron-rich source at depth to interact with water. And you need of course, the hydrogen's going to find its way to the surface anyway because of buoyancy. So, and there's just the fact that it's faulted, perhaps it helps a bit. But so Moora has all of this, and we're talking depths of 7 to 12 kilometres where we suspect, we haven't got it pinned any more closely than that. And serpentinization is generally very, does occur over quite a lot of depths. And the proximity to the Darling Fault allows migratory paths. So that's the why. And how does it manifest, and how does the geophysics, how does it show up? And Isabella and various workers came up with this term of the fairy circles. So we stick with the terminology that's become popular, despite what you might think about fairies, and we'll just go with that. So the one on the left is from Brazil, and it's about 300 or 400 metres. It's fairly circular, and you get a barren, the vegetation, it's poisons, the hydrogen venting causes a depression in the ground, and it creates these characteristic, at the top of the chimney vent, you get these circles. Oh, that's easy to find. So it's a surface manifestation of a natural hydrogen. So this is zero depth. It's happening at surface. You're seeing a chimney is formed. I'll just move on, and we'll zoom in on the Darling Fault. Now, in this particular case, the reason I'm showing it is because it's published and it's been studied, and if you get out there with your instruments, your geochemistry, and look at the gas that presents at the surface, you're getting 4 or 5 parts per million in at least half a dozen of those fairy circles. So are these fairy circles identifiable with magnetics or whatever? But let's do magnetics today. And we took third order Cauchy derivatives as a demo because we can. And it's very similar to the kimberlite type problem. So that's your Landsat or your aerial map, and then your geological map, and you go to the normal download and the area of interest, the TMI grid. And of course, there's an impact structure there, which has got nothing to do with natural hydrogen. It just happens to be there in the frame. So there's it's a famous impact structure. So the sorts of things we're looking at, this is sort of background scats, you might say, at this level. Looks like a scat. So let's zoom in on that. We just do traditional grid processing, and if you're an experienced interpreter, you know that's near surface, and you know that's sedimentary basin, and the Darling Fault's more or less here, without getting too excited about it. And the impact structure shows up, and you're getting all this background stuff there. So if we do an improved derivative, but it's still the same idea, just using a better method, you get the I'll just zoom in on that fourth derivative, and there it is. And then we say, oh yeah, it's easy enough to identify the fairy circles, and we label them A to H or whatever we've done there, and then we characterise them and have another bit of a look at it. There you go. And it turns out about half are due to farm buildings and things like that, so cultural type, so normal stuff you get in magnetic surveying, particularly around townships and farming areas and stuff like that. But the other half are the targets of interest. So that means it's sure fairy circles are easy enough to get using more or less standard practice, and so they can identify surface manifestations, and due to the proximity, half of them are cultural. So you might get a few false positives. And the other question is, why on earth is around one of these chimneys, is there some sort of susceptibility signature you can get? And I don't understand the chemistry, but there's some sort of expression of why is there a magnetic anomaly that causes that circular feature at the surface? It's there, but I don't know why. So it's some sort of geochemistry that you're seeing at the surface. So that's it for case study 1. I'm going to go further north, straight up to the Pilbara, and the very well-known early area for Rio Tinto, the Brockman syncline. So it's historic these days, but it's still the site of, I don't know if you've seen it, but there's a couple of synclines. It's this great dome structure there. It's heavily studied, very famous. It's been studied for years and years and years. There's plenty of data and there's plenty of history. But also historically, one limb of the syncline was known to exhibit a ferrous type signature, and the other limb of the syncline of exactly the same formation as it wraps around was known to be ferric. And we've known that for 15 years or whatever, but never thought much about it until this conversation comes up. Let's move along. So we record, in this case, we're not doing grids, we're doing the line data, just the ordinary TMI line data from as flown, and it's survey P509, and it's a high-grade iron ore province, so there's a hell of a lot of signal. If it's iron ore, it almost floods the instrument's ability to record the signal. Well, it does often, and which is another question. So therefore, we've got a 3D model. We're not showing that particularly, but of the syncline, and we're counting for all the stratigraphic pile, and there's the ferric limb and the ferrous limb, and you can see the lines, the survey lines drawn across it. We're going to, that's the association. So we've got a profile across it, and let's just go to work on that profile and do some of this fancy downward continuation, which is now becoming possible for magnetics. So you take a profile of magnetic data and predict what the magnetic signature is as you go below the surface. And that's starting to, well, it's still leading edge, I suppose. Not everyone can do it, but there's no secret in how you do it. You just got to have an implementation that goes ahead and does it. And sure enough, both sides of the syncline, the ferric side and the ferrous side, the character of the ferric limb is quite different, and it's stronger, and it's I've put a finger of 10 times stronger, the response, but they're iron ore minerals, and all the rest of the geology fades into total insignificance once you've got iron ore in the mix and you're measuring the magnetic response. And then, but now we're saying we can differentiate one. Yes.
So is that pure ferric, or is it like magnetized ferrous?
Oh, it's magnetized. Yes. Well picked. But I've just, that was exhibit 1, and then this method 2. So that was method 1, doing the downward continuation in the 3D. And we're back to the 3D model and the known syncline angles. And now we're doing this magnetic tensor. So we take the grid of the TMI and we transform it into the magnetic tensor. And magnetic tensors have 3 eigenvalues, or 3 arrows, 3 vectors. And it turns out once again, once the iron ore is involved, all the rest of the response fades into insignificance in the background. It's only background noise compared to the response. And all the anomalies are much more poddy than what you'd normally expect. And it's quite, where you have centres of this activity, you get so I'll just explain this a little better. I've labelled this the vector glyph visualisation of the centre of magnetisation of the magnetic anomalies, the discrete little anomalies on either side of the limb on the bractine. So the signal strengths vary a lot. And not only that, the angles that are implied on the syncline are also varying a lot. So this is great because you've got discrimination type things starting to show up, angles and magnitudes, and doing them together. We've got chance of doing quantifiable type responses here and improving our practice to go from qualitative to quantitative, because you've got actual stuff that's starting to discriminate. So just for the workflow that we did for this job, you convert the magnetic TMI grid to the gradient tensor form. You use a glyph. I don't know if you know what the word glyph means, but it's like a little symbol, but it's a clever symbol which can be adapted to the signal, the attributes of the signal. So 3 angles, 3 magnitudes, And that's what a glyph is. And we use that to show the eigenvectors, shows the angles and the strengths. And we show a little bit before and after the alteration, one limb versus the other. And the ferric form looks to be about 10 times less in susceptibility to the ferrous form. And the angles of the anomalies mostly follow the folding plunge angle. So there's also evidence. So that's remnants really. What is remnants? So it's not indicating the current direction of the inducing the world's magnetic field. It's reflecting the angles that were in the minerals at the time of deposition before the syncline even happened. So this is old. This is ancient. So it's an example of trust iron ore to be a good example, but it's a good example of showing the remnant angles as well. We're following the geology, which is unusual. And then what's the last thing there? So we're using showing the magnetic tensor gradient surveys in this context. Nice example. And just to blow up, in case there was any further need to see it in any more detail, this is all systematized. We can give you, if you don't have, you can get the data, but if you can't get it, you can ask me, I'll give you the data, give you the task files and run the damn thing yourself and check it if you want to. It's all in the box. It's not that big a deal to do it. So from the point of view of summarising quantitative possibilities, ferric form appears to be 10 times less. That's great. And the magnetic trans allows for the vector to be seen. And it looks like we're following the structural updip with the maximum eigenvector. So it's a good starting point. So, and now the summary. With the downward continuation, we image up to 1 kilometre deep, which is great. We can see all these little discrete blobs of, it's not just a consistent idealised formation. There are little blobs of more or less iron minerals in that particular form, normal. And the ferrous oxidation releases natural hydrogen. We're able to identify areas that may possess naturally occurring hydrogen without surface features. So that's more or less, and I think in going forward, I'd suggest that it makes a lot of sense to concentrate on iron ore minerals in the first instance while if this is to go forward as a sort of independent test or proof that there's something to be seen here and can be reproduced and all the rest of it. Because it's so responsive magnetically, you don't get burdened with all the other rocks saying, what about me? You can only ever see the iron ore minerals because they just dominate. So use it or lose it. Now, moving on to the radialis case, the Amadeus Basin, likewise, another extremely well-known area in Australia, and it's famous for helium. Wasn't that famous for hydrogen, but once someone asked the question, oh yeah, hydrogen's here too, and it's famous. It has been for 20 years. So there's a gas-prone source rocks in the Lower Gillen Formation. Roger. God, I forgot his other name. Anyway, the Northern Territory, Roger, helped me a lot on this when we first did it. Sorry.
Roger. We know Roger.
Everyone knows Roger.
I just can't remember his last name.
I can't remember his last name.
Thank you, Roger.
Parachuted Roger. No, he got quite excited about this as well. So, and he had a lot to say. So, so it's definitely, and he's contributed the geological extras, the Upper Gillen Formation and effective seal from the Lower Gillen. And this is about 1.5 to 2 kilometres. So we had the serpentinisation about 7 to 10 kilometres. We had the Brockman syncline at surface, and now we're sitting at about 1 to 2 kilometres. So the depths can vary quite a lot, and the geophysics is still able to make a contribution, I think. So we're getting an upwelling of the salt and gypsum from the Bitter Springs group. and the ferry circles are there. So that's the stratigraphic pile. Up a little lower, bit springs through, and it's the hydrogen's finding its way up to the surface expression through there. And there's various seismic surveys, there's 3D models, there's every damn thing in this basin. So it's a good example to come back to and have another look at. So yeah, I think I've done all that, so I won't say it all again. And of course, if you look at the Landsat, some of the bands and things, you get plenty of hits from the because at the surface of all of the salt lakes, the gypsum, and the complexity of what's occurring at surface. So any GIS is going to help you with this stuff. It's not necessarily going to help you with the deep stuff. And we see a large amount of surface expression of these vents going on in this area. It's not isolated. It's sort of everywhere almost. So I'll show you why I say that. Okay, let's move on. So let's just pick out a little bit of the magnetic, the existing magnetic surveys over the Amadeus Basin. And sure enough, in the TMI, you're getting all this scat stuff in there straight away. You think, oh God, what were the contractors doing when they acquired this data? It's got so much noise. And it's not noise, it's actually signal. In this case, it is the signal we're looking for. And so it's quite, anyway, that's another story. And we're doing the fourth order there. Well, I got those slides out of order. I should show this one first, and then the other one. Sorry. So you're getting these subcircular depressions or ferry circles there, big time. And that's the traditional fourth order derivative, which shows you nothing if you use the Cauchy fourth derivative and then do a profile through the data, which I'm going to show. And then you zoom in on the one aspect of it and just blow it up. And we're down about 1 kilometre once again, a bit over 1 kilometre. And you're starting to see these things that look like pipes. Now, you've got to check all this, but it does look as though we're starting to image the kind of some responses that are coherent and make some sense directly from the TMI data without too much trouble. And they're exactly coincident to where these scuds, these circular subdepressions. So we try the magnetic tensor enhancement here as well. Now it turns out because it's at a great depth, you know, where the action is, you don't see much. So this method with the tensor, you know, the angles and the vectors and all that sort of stuff, you get a little bit, but you don't get much like you do when it's at the surface. So it's not necessarily going to be that effective. And the other thing that's been tried is to marry the downward continuation with the seismic line. It's been so instead of just relying on seismic alone, the whole idea of using multi-physics, of course, should be, if you can do it, should be used because you know one complements the other. So in this case, we conclude there's radiolysis. I don't think that's controversial. And due to the presence of this salt in the upper strata and other salt traps, there is potential for a natural hydrogen seal and reservoir in this area, not surprisingly. And one way is to try and see if you can start imaging the potential cap rock and seals and all the rest of it. And the other curious thing about this situation is the gypsum that Roger Clifton finally pointed out to me in great detail and saying the Northern Territory government distributes a map of all the gypsum occurrences in the Northern Territory, unlike any other state or federal department, and driven by pure curiosity. Why is there so much damn gypsum and around associated with this on the surface when all this activity is going on? I'm not a geochemist. I don't know completely the answer, but I point to your attention that is also another indicator of this activity. So now, having done the three stock standard, easily achievable Australian case studies and test cases and saying, oh yes, there's enough here to give us confidence that we should sort of invest some more time and effort in that. Because I'm going to Namibia to give this talk, I thought I'd better wrangle in the possibility of a Namibian case study and blow me down. And I talked to Isabella about it. She said, oh, I'm glad you asked. There's a paper in Science Direct available online. I've got all the references here. Just released of all the activity in Namibia and the prospectivity. So I begged, borrowed and stealed a little bit of that and included in the talk. And we're in a as usual. All geology can be quite complicated. You've got the Congo Craton up here. You've got the Kalahari over here, and that's the section line, and that's a schematic, a classic schematic. And the Waterberg Basin is identified. There's the thrust lineaments as being quite prospective. I don't actually know the story about whether there's leases or there's current exploration activity. I'll find out in a couple of weeks, I'm sure, or in this area. But it's certainly being led by European interest in getting into the field and making the case for it. Damara Belt. So it turns out Rainer Wackerle and Dave Hutchins years ago had put this, they'd hell-bent on replicating Australian best practice in airborne geophysics. So lo and behold, there is a good TMI compilation for the whole region, and it's been around for nearly 15 years, or 16 or 17 years, and it's high resolution, and therefore it's suitable for the same sort of treatment that I've shown what we can do in Australia in this area. And there's banded iron formation that I somehow dispute this quote. It seems unbelievably optimistic that the banded iron formation constitutes more than 60% of the global iron ore reserves. Really? But that's the quote from the paper. I find that very hard to believe. Anyway, I left it in just for everyone's to contemplate that particular thing. But there's every possibility that there's natural hydrogen occurring there as well. So let's start to wrap this up and talk about and go to a couple of discussion points and then a conclusion. So moving to a quantitative method for redox using magnetic remote sensing shows promise. And you can see you can characterise the different magnetic response if you try a bit harder. When hydrogen production is occurring at great depth, you really only get the chance to see these chimneys or vents. Typical airborne geophysics isn't going to see stuff that's with any sort of precision or detail at depths, greater than 2 kilometres or stuff like that. You're going to have trouble. So you're stuck with the fairy circles. And vector display methods are applicable. Yeah. And you should use that because that gives you ability to give more character to what you're seeing. And I personally recommend, again, bang, Australia should be doing magnetic tensor gradient surveys. How come we're 10 years behind the rest of the world? Unbelievable. That's my plug. It's available commercially, and we've not done one of them in Australia. There's the current step change. Louis online. He can probably kick me in the guts for putting this slide up, but De Beers have spent all this time in the last 7 years. That's your typical crop duster with the TMI. I'll just keep going with the little bits. So you've got 2 total field indicators either side, TMI, and then in the stingers, the large stingers, one of them's got the full tensor, the helium squid full tensor magnetometer, magnetic gradient meter, the IPHT squids, which have been coming to Beers as sponsored and championed that for 15 years, Eddie Coslin in particular. And it's available for commercial release, I've been told by Henri. And it's not quite, I believe it still has some issues to sort out, but it's a pretty good start that it's actually in a plane finally and airworthy and ready to go and all the rest of it. So I think the sooner we get one of those type surveys in Australia, the better. So my conclusions, aeromagnetic geophysics has been effective in showing manifestations, surface manifestations in the serpentination context. There's possible historical hydrogen production due to redox at the Brockman syncline because of the weathering, and the migratory paths in the Amadeus Basin look like there's a way of spotting that due to radiolysis. So the three mechanisms I've proposed all seem to have the geophysical response, no worries. So while most discoveries to date have involved field work, I think we can insert geophysics in front of that and try and get a better early discriminator as part of the regular workflow with follow-up. Followed up by multi-physics and SEALs and all the rest of it, and perhaps bringing in existing seismic data if you've got it. So that, as in the words of Bugs Bunny, that's all, folks. So any questions? I did, I had some off-the-cuff comments that I wrote on the plane coming up in case there aren't any questions, but if there are questions, maybe I'll do the off-the-cuff. So I've started to cover this, that, you know, in all these examples, Australia is blessed with all these 3D models and integrated geology and geophysics studies, and if you're lucky and you use the right tools, these can be automated and, you know, do uncertainty studies and the whole works. That's an emerging field. I've been at the middle of that for a while, and so all those examples come from such cases, and they're all pretty much freely available. So geophysics, magnetics, gravity, gamma rays, and the electrical methods, I think, are all potentially able to be worked into these workflows. I don't see why not. I'm just trying to point the way ahead and try and generate some enthusiasm for people to follow. And the three depth settings, the surface, 2 kilometres and 7 or 8 kilometres, they're all viable, that you can get something from them. I don't think that's a problem. What's missing, however, in the arsenal is the nuclear, some idea of trying to work out how do you model nuclear physics and radiolysis and integrating that with geology and geophysics. We've never tried to do that, to my knowledge. And also, of course, the big missing element in Australia is that how do you get geochemistry in its 3D setting, especially at depth. No one does much geochemistry at depth. Anyway, I'll just say that, whether it's true or not. And so the framework for doing automatic builds is there. All the tests, these tests I've shown you are also available. They're in the public domain. Yeah, I've already said that. And the other thing that's missing, of course, is groundwater. And you'll note that every time we talk hydrogen, water's involved. Therefore, groundwater is very critical. And our practice. Okay. Mark, yep.
In the Murray example, how many flight lines were crossing the average sized ferry circle?
In the
Murray example.
Oh, Mora.
Yeah.
Yeah. Thanks, Mark. I showed in the Mora case, it's regional magnetics. It's this standard regional Western Australian, North Perth Basin stuff. So it's, I think it's 200 metre line spacings in the normal manner. So the answer was we used grids in that case to do that work. We didn't actually use flight line. I showed flight line data for Brockman and I showed flight line data for Amadeus. I didn't show you the flight line data from Mora, so well spotted. And it does lead to the question, do you get better results by doing profiles off the flight line data and I think you do with the Cauchy work, so the practice is evolving to sort of stick to the profile data, the observed data, if possible. I don't know if that satisfies Mark. We can try.
Is the Cauchy an alternative way of performing a fast Fourier transform, or is it more than that?
A fast Fourier transform's implicated everywhere in the. Try and give you an exact answer. You upward continue to do Cauchy in the workflow. You upward continue using a fast Fourier transform at equal intervals, like every 5 meters or something. You do 10 upward continuations, and then you draw. Generally, we draw a circle. I'm not showing you the right bit of graphics here. It's in the other talk. And then you go around. Cauchy. All Cauchy does is integrate around a closed circle, and the complex number of the upward continued is fed into the function, the analytical function, which will yield whatever derivative you want. So Cauchy is famous for creating derivatives from integrated upward continued fields. And Fourier transforms are in the middle of it. The only thing you're not using a Fourier transform here for is downward continuation. You're using what's called, it's not a Taylor series, it's a twin Taylor series called the PAD complex number series, but it's equivalent to a Taylor series because you've now got reliable, or more reliable. I won't go nuts on that particular statement, but you can create derivatives up to the 7th or 10th or 11th order, which are coherent, remain coherent, which is the thing that's completely different to what we've been used to.
The upward continuation
is stable.
Downward continuation.
Downward continuation is not stable, Fourier methods, but upward continuation is.
And is it still based on Laplace equation?
Yeah. The physics doesn't change, except, so what bit of physics is new? There's no new physics here. It's just, you're just cutting out a first approximation and substituting a better mathematical method for creating derivatives, calculating derivatives. You haven't changed the physics.
You had your, like a pseudo section.
Yeah.
Where you're.
You haven't seen this before?
No, I haven't seen any of it.
It's in preview, mate. Yeah.
I think April's issue's just arrived, so I'm waiting for the next one now.
That's in the leading edge. So
For everybody new here, Des and Ned go back a long way.
that's fine. I don't care. Knock yourself out. No, it's just seeking clarity, and I enjoy that. So,
But I guess my question is, I don't know what you called it, a pseudo section, but
I call them depth sections.
Okay.
But it's just like a depth section, like any other damn depth section.
But it did seem like it was just smearing the fairy circle down. Look to me like if you're basing it on magnetics, which is a potential field, how do you get the same resolution at the bottom of your section as you are at the top?
Well, So look at the numbers as you do higher and higher derivatives. These bloody numbers become tiny compared to what you started with. 11th derivative or a 7th derivative of the signal is pretty damn tiny numbers. So of course you're exposing more. So the quality of the TMI survey. So that's why I'm recommending, and I have personally, in my own time and in my own way, worked out how to do downward continuation of the gradients, of the full tensor gradients, and that's the other paper, and exploring that. And then if you measure, so you're back to do you measure gradients? The old hairy chestnut. Is a measured gradient better than a calculated gradient? And historically, potential field gradients that are measured are always better, but Cauchy tends to upend that because you are actually able to get a measured gradient using Cauchy, which remains coherent. But despite all that, I think the measured gradient and I think the magnetic tensor gradients are great in showing promise. And so can you image discrete? So some of the options we show in our papers, which you haven't, I'll send you copies of them, show discrete anomalies as you go deep. They don't just follow the pipe. You get a form, you get, you know, the end of the syncline, you get a bloody anomaly perfectly, and it's a bullseye at depth, and the gradients can show you that. So like the other, yeah. So the paper that we published at the ASEG Brisbane has exactly that example in it, and that's the one for Peepers Creepers. The I've just forgotten it. Anyway, so it's a mine in Queensland where we've got all those examples.
In the extended abstracts for the last
Yeah,
conference.
yeah, no, that's all there.
And you referred to it in the
Yeah, I remember.
sliding doors paper.
Yeah, of course I
which is an excellent paper.
Thank you, Ted. You're so kind. Compared to Ned.
But can I make a comment?
Please.
A general comment. I think Augustin Louis Cauchy in the afterlife would be rather perplexed when if he hears that you're using his mathematics to look for fairy systems. I'd also say, you know, given my past history in government, to take forward a case to invest in further high resolution surveys using tensor magnetics with the application of Cauchy, etc., to government, and also for industry to take things to the stock market. Talking about fairy circles ain't going to work.
No.
So we really need to change it. So when you go across to South Africa, I'd ask you to take a vote from all the colleagues in all our colleagues in Southern Africa what they think it should be called. There needs to be a chemistry base like hydrogenation circles or something that signals what the process.
Are acceptable.
They're far more acceptable. I also think, just the general comment, also think this is really exciting if this attracts more science to go and have a look at what are the real processes, particularly the nuclear processes, that create hydrogen in the earth. You know, what are the complex mix of processes? That has all kinds of interest for the other side of producing hydrogen, you know, from other processes on the surface. At the moment, South Australia's got a pilot plant to produce hydrogen with the concept of scaling it up. The power would come from a massive big solar energy system.
Yeah.
So if we better understood the whole chemistry of how hydrogen is produced natively in the ground, there might be some other simpler, lower energy processes that can generate it.
I agree with you, Ted. When I looked for sensible reference material for radiolysis for Earth processes, I couldn't find anything much. You know, sorry, I've got Chris in the room. Please speak.
It is what you say.
I know, and so I just skimmed over it a bit. But I agree with you. That's why I mentioned, I think there's a need for, just like we systematise, you know, groundwater in the context of 3D geology and how it links to the EM and whatever, we need to sort of think about the possibility of these nuclear, some models for what's going on with the nuclear style reactions at depth. The only thing you seem to see is people getting excited about the cooling water in nuclear reactors, getting hydrogen byproducts from the water that's being used to cool the cores. There does seem to be work on that, but I didn't bother to try and reference that.
Thanks. Yes. I was just wondering, about the ferry circles. So in southwest WA, there's a whole bunch of circular features at the surface that look like lakes. So I've looked at a lot of them to see if there's sort of a response in the airborne electromagnetics to what, could be the ferry circles for, natural hydrogen seepages. And it's really difficult to actually separate them from just regular lakes. And I was it's really good to see that you've shown that they have a magnetic response. I did look at the mag and grab and stuff in that area, but I didn't really see much of a magnetic response. My question is, how would you separate, say, maybe something like mag heat might forming in a depression in the at the surface, which versus something that's related to helium, hydrogen, coming up to the surface.
I think it's I tried to explain that in my own humble way or silly way. I thought, yes, you've got deep-seated radiolysis, which is causing the hydrogen to vent. But what you're seeing at the surface is a sort of a secondary process where the hydrogen, as it vents at the surface, somehow is affecting the minerals around the periphery of the vent, and you're getting a susceptibility contrast at the surface. And as far as I can tell, I don't think anyone's gone out there and with a susceptibility meter yet around these fairy circles and tried to figure out what's going on.
Okay. So those anomalies, they look like they're right at the surface.
They are, clearly. So, or with the water table or right at the surface. Yeah. I agree. And I've tried Isabella on it, and she had nothing to say. And I've recommended, who am I? I can just make these observations, sort of put it out there and see what happens. So
I guess it's good to see that there's further information that people can use.
Yeah. Now, on your question about AEM, I started to think about it, and we've actually got form in AEM and, high quality inversions, and I've put a lot of effort into it, but we haven't actually tried it yet. I'm trying to see if we can. So I'm trying to work out how to flog AEM processing practice to improve it. So we've done that by investing in what's called the 2.5D method for AEM inversion, finding all the bugs in the old original code that was CSIRO did, and we fixed all that up and then optimised and all the rest of it. But it's still some people love it, and lots of people just want to ignore the fact that you've got a better method because it costs you money to use it. But forget about the money. I think we should just concentrate on a sort of a scientific, like you're saying, somewhere if there's Western Australian case study where there's a decent bit of AEM survey over one of these features, we should work it up and have a bit of a look at it. And I'll do it for nothing for you, no worries.
So what's the AEM expression?
It typically looks like just your regular lakes as well. So the lakes in that area are very conductive. And what you see is in the conductivity sections where the lake exists, you've got a conductive feature, and that tends to sort of lead down into a lower mid-level conductor as well, and taper off. So that could be saline water sort of seeping into the ground or something like that. Mix of the clays, or don't know, but it's hard to separate those features over places that people have identified as fairy circles versus what a lake, circular lake, looks pretty much the same in the aerial imagery, and it's pretty much the same in the AEM as well. So
there is a case study. There's one in South Australia, the Lake From case study, where we put Benthour back and worked pretty hard on it. There's a 3D model and the whole works. And there's not allowed to slag off the contractors and their data remote. I won't do that then. But there was a lot of trouble with the data as delivered in that case to try and get a comprehensive, to invert both the X and the Z and make it, the Y and the Z, sorry, as you go down the line and getting it to work properly in Lake From. It's very difficult. And so sometimes, and of course, in a Lake From setting or like the Western Australia, it's very salty. And of course, that's a shock. That's very difficult to get much out of if you're trying to get any penetration with depth, because the salt's so damn conductive. And you get, I know you got some. AEM's not. It's not a straightforward challenge. It's complicated.
The real strength is integrating with the other data sets and just showing that magnetic stuff that you just showed.
Yeah, no, you can do it.
Just helps you build that confidence.
Yeah, you dodge most of the bullets, all the problems that you get with AEM in this context. got salty.
Yeah, so
Sorry.
use of fairy circles, I wouldn't use that.
Just forget about the term.
I think it was coined to get people's attention.
It did. And it's upset certain people straight away.
So you sort of had it in there. You had
SCDs.
SCD, yeah, subcircular depressions.
Yeah.
Because the fairy circle as defined is not that. There is a
There's a formal definition.
yeah,
Yeah.
there's a form
Where
definition.
mushrooms or something.
So the fairy circle, sort of semi-arid.
The vegetation.
The vegetation, you could have termite mound.
Oh, yeah.
Like this in here. So yeah, so
Let's keep it out of the
there actually
geophysics.
is a formal definition of
All
a
right.
fairy circle. It's not
Okay, I agree.
nothing to do with that.
All right, I'll remove it from my talk.
Oh, you can have it in brackets.
All right.
So with the other one, I was interested in your comment about on Kangaroo Island that it's still flowing.
It's been tested in the last year. Again.
Well, I think that's probably onshore in the York Peninsula, the Gold
No, it is on Kangaroo Island.
Ramsay Well, so that's onshore. I know Kangaroo Island, the South Australian Department had that well offshore
Yeah.
to start with. So it's the Ramsay oil bore.
Yeah, that's the one. Yeah. No, you're right. You're right onto it here. I can tell.
That's not on Kangaroo
Are
Island.
you aware of the difficulties with land access that's going on at the moment in Kangaroo Island? A lot of aggro from the landholders. Yeah.
So with the modelling of radiolysis,
Yes.
it has been modelled. So you sort of, you know your concentration of potassium, thorium and uranium, the radioactive half-life decay, so you can work out the energy. Sort of 99% of that energy is dissipated as heat. And what's left over, sort of a stopping factor they use, and then that energy is available to decompose water. So you have to know, you have to have porosity down there, and work out your volume of water, and so that's with that that map you showed of the hydrogen rich or the natural gases. There is one where we did use the radiogenic map of Australia to model the rate of hydrogen generation, radiolysis. Yeah, but that's just for the surface, so you can extrapolate it to the subsurface.
Maybe.
Maybe.
I know about that.
You can do a back of the head calculation, but you really need techniques to know what's on the subsurface. But we just come off about 6 field surveys in New South Wales where our for soil gas sampling, one of those was that we sampled some sort of subcircular depression, but we did use magnetics, EMI, and the first vertical derivative from Mike's magnetic map of Australia. So it actually is being used.
Of course.
But
It's generic. It gets used everywhere.
not at the level,
Like
not in
this.
the detail that you.
No. No, I think that goes to the question. It is a generic tool used by just about everyone because of its versatility and its accessibility and all the rest of it. And that's great. It's exactly what that data set's supposed to do. And it's overdue being, I think there's a new New South Wales version and there's a new, so every 2 years there's a new generation as the data sets improve and all the rest of it. That's an ongoing process as you get better data. So is that near the Cobar block? As you talking about? I've got some reason or another Cobar's coming into my mind.
No, for the Cobar, with the Tumut.
Down.
So that's got the Kuvac serpentinite.
Yeah.
And then in far west New South Wales, you've got the
Windy or
line
something.
formations out there.
I know.
So, and we actually did see but not in every area, but there is on the edge of the magnetic anomaly, we do see elevated concentrations of hydrogen
Thank you.
and helium in the.
All right. When's that coming out?
Helium and hydrogen are
No,
together, high concentrations of helium in different areas.
the
Hydrogen. Yeah, well, yeah, that record is under internal review at the moment, so
Yeah.
it should be out very soon.
So we'll go to, can you shoot me a copy when it's done? Sure. That'd be great.
Say we have refreshments at the back of the room. We can continue the conversation while having those. Okay. So, thank you.
Thank you. Second.
I can give you both.
Because he went to come last week, but that showcase was on it. He wouldn't, so he's just come down. It's up with the next. What are they doing?
I do.